Today we get to talk about nuclear physics. I hope you like that subject. And specifically, we need to know more about these nuclear orbitals. Great comment. And let's talk about them. So hopefully you understand the concept of electron orbitals. A lot of people don't. If you think of electron orbitals like planetary bodies in orbit, or moons around a planet or something like that, that's not how it works. They're more like clouds. They're clouds with angular momentum. And to put that succinctly, basically you have the electron, which itself is a cloud. It's a wave function. It's got a probability distribution, meaning all that you can really say is the likelihood of seeing an electron at a given location or seeing an electron with a given momentum. That's really all you can do, is come up with empirical estimates that observation does demonstrate and validate. Is you can come up with estimates on what is its momentum and what is its position, and also spin or any quantum variable, any property that it can have. It's a probability distribution. And so that probability distribution, it is subject to all of the laws of physics. And so if I have an electron orbiting a nucleus, I make the approximation that the nucleus is a point source, like with a hydrogen atom. If I say that the proton is a point source with negligible distribution, it's literally just a point source, and the electron is now attracted to it through the Coulomb force. The proton has a positive charge, the electron has a negative charge, and now we treat it as a wave function. What ends up happening is that the wave mechanics require that the electron can only have distinct energies in a stable orbit. And why that's significant is that those are the energy levels that we actually see in material. You can calculate it exactly with hydrogen. You have to use more and more approximations as you get larger and larger nuclei. But you conserve angular momentum. You conserve linear momentum. That's rather trivial. You conserve energy. And when you do that, you say it's also this wave distribution or a wave function, then there are discrete energies that it can have. Those are the quantized energy levels that you can have. And you don't get those unless you have this point source charge. Once this charge becomes distributed, it becomes more complicated, and you can't do a closed form solution. You got to do numerical approximations and so forth. And that's when you have an electron that's attracted to a positive nucleus. Inside the nucleus, you have protons and neutrons. Now, all the protons are repelling from each other, and the neutron from the Coulomb force, and the neutrons are not repelling. They all have the strong nuclear force, and they're all holding each other in there. Now, that doesn't mean that they are not subject to Schrodinger's equation. They still are subject to Schrodinger's equation, but now the boundary conditions are much more complicated. I don't have a point source with a cloud out here. Now I've got a distributed source, and everything is within that distributed source, so that the Coulomb force literally goes away at the center of the nucleus. A proton in the center doesn't have Coulomb repulsion. It's basically everything's pushing it equivalently, and so it's not feeling a net force from the other protons in the nucleus, but it still feels the nuclear force, and everything's holding each other together. To make it worse, the nuclear force is attracting, all protons are attracted to each other, and neutrons are attracted to each other, and protons and neutrons are attracted to each other through the strong nuclear force. Except for out on the outer ridge, you have a disequilibria, because on the outer ridge, now everything is pulling on each other, but there's nothing out here pulling out to equalize the forces pulling in from this strong nuclear force. And so you have a tension there. It's the same thing happens on a water droplet. All the water molecules are attracted to each other in a droplet, but outside the droplet, there's no more water out here pulling the molecules on the surface, and that's what creates a surface tension on a water droplet. So you have that. You have the fact that they all have to meet the Schrodinger equation. What's worse is it's the relativistic version of the Schrodinger equation, which is far more complicated, but it still leads to quantized energy levels. And angular momentum still has to be conserved, and energy is conserved, and potential energy has this distribution. And so when you look at that, you still get quantized energy levels. They're just far more complicated. And the only one that you can really solve, say, in closed form is deuterium, a proton and a neutron. And there you can solve that in closed form. It takes a few pages of calculations to do that. But when you get much more complicated, just like with other atoms, you start to have to do numerical approximations. So that by the time you're at massive atoms, like uranium or something like that, you just model the whole thing as like with a liquid drop model, because it actually will vibrate as though it was a liquid drop. The resonances, the different frequencies that you get are the same pattern that you get from vibrations of a water molecule. And so it's far more complicated, but the bottom line is that the energy levels still are quantized and they still have orbitals. It's just you've got to do a lot more calculation if you want to approximate those. So the same physics, is just now everything's relativistic. Plus, you've also got to throw in the Heisenberg uncertainty principle. That becomes non-negligible there as well. So it's just a lot more complicated in the nucleus. But physics is the same everywhere with the orbital electrons and in the nucleus. It's just there's a lot more going on in the nucleus. So great question. I hope that answered it. I hope everybody learned something and enjoyed the video, and I hope you all have a good day.